Okay, we're going to pick up here. Actually, I think we're back here. This is where we left off on the last video. We had been introduced to a new chi-square significance test called the chi-square test for homogeneity. And the key there is we are trying to compare whether there is a difference between the distribution of one categorical variable, but across multiple populations, or two or more populations, two or more samples. So when you're reading these problems, you want to see if it sounds like there were multiple samples taken as opposed to just a single sample taken from a single population. If we're talking about multiple samples, it is going to be the chi-square test for homogeneity. So here we have 4 random samples. It opens with telling us that we have 4 random samples. That's very important here, of news viewers from the networks ABC, CBS, NBC, and PBS. They were taken in a particular city, and they were asked about their political affiliation. The results are displayed below. So here are the 4 populations, viewers from each of those networks, and so this is definitely going to be a chi-square test for homogeneity. You can see that the categorical variable that's being measured is basically what their political affiliation is, liberal, moderate, or conservative. We have our column totals here, our row totals here. The grand total is 300. Okay, we're just going to fill in a few things here. I have the template sort of set up for us here. Obviously, you would be recording all of this information that I have pre-typed here for this PHANTOM acronym. But I think the key is trying to make sure that we're studying and memorizing how these hypotheses differ from one chi-square test to another. If we're talking about the chi-square test for homogeneity, remember homo means same, we want our null hypothesis to say that there is no difference between the distribution of, here's our categorical variable, political affiliation, for these populations, the network news viewers, versus there is a difference between the distribution of political affiliation for network news viewers here. Okay, now this was not an experiment. There were no treatments being imposed. In fact, it told us clearly right here that these are samples. So that means when we are listing our conditions, we do have 4 of them that we have to go through. You can see I like to package these 2 together in one sentence. Samples were taken randomly and they were independent of each other. If we were going to do the 10% condition, because we actually have 4 samples here, we would have to show this 10% condition 4 times. I'm just going to show the first one here. 10 times 80 be 800. I believe that was from the news network ABC. So we would need to say that's less than or equal to all ABC viewers. Okay, we would do this for each of the networks, 10 times 95, showing that each of those is less than or equal to all of that network's viewers. Okay, I'm just going to kind of jump around on this without even filling everything in entirely here, because I think we've done so many significance tests that we kind of get the idea. Okay, one thing that would definitely have to happen for our third, or I guess this is really our 4th condition, is we have to make sure that we have shown a matrix off to the side here listing what the expected counts are. Remember, the expected counts to get each value in the cell, you take the row total times the column total, divide that by the grand total, and we never round those. Okay, if you list them in a matrix, you don't have to relist them again. You can just simply state that the large counts condition is met because all of the expected counts are greater than or equal to 5, and you can simply just draw an arrow to that matrix showing that all the values that would be in that cell there would all certainly be greater than or equal to 5. Okay, we definitely want to name this as the chi-square test for homogeneity, and I would encourage you to use the chi-squared test command on the calculator. That does mean that you do have to go into matrix A. This would be a 4 by 3 matrix, 4 rows, 3 columns. 4 columns, 3 rows here. Okay, and you would input all that data. Okay, and then in matrix B, you would put all the expected counts. Okay. One last thing I just want to fill in on this one without filling in all the remaining parts of this is, don't forget, for these problems that are presented in tables like this, the degrees of freedom are always number of rows minus 1, so we had 3 rows, so that would be 3 minus 1, 2, times number of columns minus 1. There were 4 columns, minus 1, that would be 2 times 3. Degrees of freedom would be 6. Okay. All right, that could be ran on the calculator there. Let's just go ahead and look at the next example here in the notes, talking about cell phone users. It says random digit dialing telephone surveys used to exclude cell phone numbers. If the opinions of people who have only cell phones differs from those of people who have landline service, the poll results may not represent the entire adult population. So the Pew Research Center interviewed separate random samples. So we see here that we're talking about 2 separate random samples, one of the cell phone user group and one that's exclusively the landline telephone user group, who were all these people were less than 30 years old. And here's what the Pew survey found about how these people describe their political affiliation. Okay, so once again, what we have here before us is 2 different samples that were taken from 2 different populations, and what we're measuring is we're essentially measuring one categorical variable, that categorical variable being that person's political party affiliation, if they're Democrat or lean more Democrat, if they refuse to lean either way, or if they're Republican or lean more Republican. Now these percentages that you see that I have filled in here, this represents the percent of just the cell phone group who are more Democratic in nature. You'll notice the sample sizes are different. There was 96 from the cell phone group, 104 from the landline group. So I got 50% by dividing 49 by 96, 15 by 96, and 32 by 96. Did the same thing over here, so I have the percentages. Okay, the reason I wanted those percentages is in part A, it's asking us, and this is what we would have been asked to do all the way back in chapter 1, it's asking us to compare the distributions of the political party affiliation for cell phone users versus landline users by making a graph. You can do a segmented bar chart. I tend to gravitate towards these side-by-side bar charts. Typically, you have to make some type of legend off to the side. I made each bar represent Democrat, refusing to lean either way, or Republican. Assigned some shading to each of those. Always labeling your axes here, and then I use these percentages to determine the height of each of the bars. Now, typically, what we would do here next in this problem, we would want to fill in, for this problem, our hypotheses. Okay. Now, when we're doing the hypotheses for this, your hypotheses are determined by which type of test you're running. Now, remember here, we said we were taking 2 separate samples, so that was an indication that this is definitely going to be a chi-squared test for homogeneity, which is when we say there is no difference between the distribution of political affiliation for cell phone and landline users versus there is a difference between the distribution of political affiliation for cell phone users and landline users. Okay. Now, I'm not going to talk through this entire problem, but if you're interested in having another example in your notes, you could pause this video and go ahead and record the remaining parts that I have here for this. You'll notice I did do the 10% condition for each of the 2 separate samples here because they were different sizes. And then the rest of it hopefully is self-explanatory there. You could pause and copy that down if you like. Okay, so what we're going to be introduced here in the next page is the third and final type of chi-square test. This is called the chi-square test for association, or it could also be called the chi-square test for independence. I find that on a lot of the AP rubrics, seems like people generally gravitate to naming it chi-square test for independence, but either is acceptable. I think the word association comes into play when you're drafting the hypotheses for this type of test. Okay, so let's take a closer look at this. I know these tend to get confusing, these 3 different types of chi-square tests. I think how you're able to tell which kind of test you're going to use is you need to think through how the data collection process took place. Goodness of fit was from one population, and you are only comparing one categorical variable. Chi-square test for homogeneity is one categorical variable compared across multiple samples, multiple populations. And the chi-square test for independence is now you're testing to see if there is an association, but look now, we're testing to see if there's an association between 2 categorical variables, but we're now back to from just a single population. So this is just a single sample, but we're comparing to see if from that one sample, if these two different categorical variables are in any way associated with each other. Remember what independence means. It means that if you know one category or factor about someone, it could in some way influence or tell you something else or another category about something or someone. Okay, so the key point here is we're talking about one sample from one population, but we are measuring two categorical variables. Now, what you're going to notice about this test is the mechanics of this test are exactly the same as how you run a chi-squared test for homogeneity. It's actually even the same calculator function. It's just that same function, which is just simply called chi-square test on the calculator. Okay, now the key is this type of test also lends itself to presenting itself as a two-way table. So we have to be careful. When you see two-way tables, it doesn't necessarily mean it's always going to be a chi-square test for homogeneity. It could be a chi-square test for independence, okay? So let's take a look at how the hypotheses are drafted for this particular test. Okay, there are two different ways that you can word it. I kind of prefer the first way here, which is we want to say that there is no association between the two categorical variables in the population of interest. Remember, your null hypothesis is generally a statement of there's no difference, or in this case, there is no association whatsoever between these two categorical variables in this one population versus the alternative, which is saying that there is an association. Okay, there is an association between these two categorical variables in this population. Okay, another way that it could be worded is just saying the two categorical variables are independent versus they are not independent. I like to kind of stick with this because it keeps that same, there's no difference or there's no association as our null hypothesis. Now you'll notice we are back to just three conditions to check. We don't have to add that fourth condition, making sure that each sample is independent, because we're not taking two samples or more than two samples. We're only taking one sample here, and we're comparing two categorical variables within that one sample. Okay, so let's take a look at the bottom here. The chi-square test for homogeneity versus the chi-square test for independence. Also can be called the chi-square test for association. Okay. Now, these tests do look very much the same. Okay. Although they do look the same, what they do is they answer a very different question. And so I think the big thing that is different is they have different hypotheses. Okay. How you draft the hypotheses is different. How you execute running the test is the same. So the test for homogeneity, okay, this tests whether the distribution of a single categorical variable is the same across several populations, versus the test for independence is measuring how two categorical variables are associated in a single population. Okay. A lot of times questions can be worded kind of poorly. I like to think not on the AP test, but and they're worded in such a bad way that it's kind of difficult sometimes to tell the difference between these two tests. And so if you could focus on what you really want to try to hone in on is how was the data collected from one sample or more than one sample. If it's a single sample, we're doing test for independence. But if we're talking about multiple samples or an experiment, multiple treatments, it's the test for homogeneity. Okay, so we're going to wrap up this video by looking at one example. Okay, one example of this new test here. Okay, it says what we're looking at here is we're interested in the length of people's fingers. It wants to know, is there a relationship between someone's gender, that's one categorical variable, and what their finger length is? Now it says a random sample, that's singular here. There was only one sample taken. A random sample of 452 U.S. high school students completed a survey. The two-way table shows, now look at what the two-way table shows. It shows the gender of each student and which finger was longer on their left hand, their index or their ring finger. Make a well-labeled bar graph and compare the distributions of finger length for females and males, and describe what you see, and then run a test to verify your observations. Now, I already have some segmented bar graphs here for us, but you'll notice there was one sample taken, 452. They did not take two separate samples, one of females, one of males. That was described, I knew that from up here in the directions. Now, once they had the 452 people, they sorted them by female and male, but they didn't draw two separate samples. It was one sample. That's the difference here, okay? Now, you can see we have one sample. Our two categorical variables are gender across the top and which finger was longer, finger length here, index or ring. So we're going to look at this segmented bar graph here at the top. Okay, you can see, you could organize it either of these two ways. You could let each of the colors represent, like this one on the left, the length of the index fingers, which one was longer, and across the bottom you could do the gender, or you could let your legend be the gender and across the bottom do the length of like which finger was longer. What you'd be looking for here is what we tend to notice, and this is what we did only in chapter 1, before we had this chi-square test for independence, is we tend, if there is no association between the two categorical variables, we expect that these percentages to be virtually the same in each of these categories. Now, what I'm seeing right here, and I'm just going to use the blue index finger from this first graph here, it looks to me like we're talking about 40% of the females have an index finger that is longer than their ring finger. But then when I look at the males, they're down to only 20% of their index fingers are longer than their ring finger. Now, I'm getting the hunch here when I look at this that if you told me, all I'm going to tell you is that someone is a female, that would lead me to believe that their index finger is probably longer than their ring finger versus if it was a male. So if I know one thing about one of the categories, it kind of tells me something else. Okay? Or if I just told you, look, this person's finger, I'm not going to tell you if they're male or if they're female, but this person's index finger is longer than their ring finger, I would tend to suspect that that person was probably a female. That's what we mean when we say there is an association probably between the two variables versus if there's no association, then you're not really given a hint or an inkling of what their gender would be based on knowing that the index finger is longer than the ring finger. So I'm going to draft up here, since the sections on the bar graph for finger lengths are not the same for males and females, there is likely, now I'm just suspecting this here, there is likely an association between finger length and gender. These are my two categorical variables. Okay, so I'm suspecting that, but I really need to run the test to have a concrete conclusion here. Okay, so here's how I'm going to fill in these blanks that we have here. Our null hypothesis is going to be there is no association between gender and finger length, index finger and ring finger, and then there is an association between those two things. Alpha level will be 0.05. You can notice here I said the samples were taken randomly. My 10% condition, it was only one sample, so I'm just doing one of these here. Certainly 4,520 is less than all the U.S. high school students in our country. Okay, I'm going to go ahead and fill in our expected counts here. Now remember, this is row total times column total divided by grand total. Do not round these. Okay, I'm going to go ahead and fill in these numbers, but hopefully we've done enough like this that you're seeing where I'm coming up with these numbers. Okay. All right. I'm going to make the remark that all those expected counts are greater than or equal to 5 and draw an arrow. Okay, the name of this test, chi-square test for independence. Now, I will tell you here that if you cannot keep straight what the name of the test is, it is okay for you just to call it a chi-squared test, because that's what you're selecting from the calculator. Okay, I'm going to draft just the first couple calculations here. Observed minus expected divided by expected. But I'm really going to run this on my calculator. Okay, so what I would do is I would put the observed counts into matrix A. I would put the expected counts into matrix B, and then I would run the chi-square test. It would give me that the chi-square test statistic is 29.02. It actually is going to report to me the degrees of freedom as well. We know that that's number of rows minus 1 times number of columns minus 1. That would be 2 minus 1 times 3 minus 1, which is essentially 2 degrees of freedom. Okay, the p-value that should be reported is super, super small, like a lot of zeros here. 1, 2, 3, 4, 5, 6 zeros. That virtually rounds to 0. And here is my decision here to conclude and wrap this up. We're going to say since the p-value, which is 0, is less than the alpha level of 0.05, we are going to reject the null hypothesis. I'm going to say that in this instance, and this is what we suspected seeing in those graphs up above, that we feel like, okay, now we can say that we have convincing evidence that there is an association. Remember, we are drafting, we're going with the evidence is always in favor of the alternative hypothesis, that there is an association between gender and finger length. Specifically, that was index and ring. Okay. You can see a few problems here that you can go ahead and try and practice this chi-square test for independence.